Okay, this is a video of me going through the Year 13 Maths Mechanics paper from the March mocks in 2022. Okay, so question number 1. A particle P moves with constant acceleration. At time t equals 0, P is moving with velocity 4I. And find the velocity of P at time t is 2 seconds. Okay, so to go from acceleration to velocity, we need to integrate with respect to time. So we're going to end up with 2 minus 3 times t plus a constant vector. Unknown vector, let's not use A, let's use constant vector C. This is like an arbitrary constant from the integration. And we know that when t is 0, it's moving with 4I. So when t is 0, we want v to be 4, 0, so therefore c must be 4, 0. So v is going to be equal to 2 minus 3t plus 4, 0. Okay, this is part A. Part B. At time t equals 0, the position vector of P relative to fixed origin is I plus j. Find the position vector of P relative to O at time t is 3. So again, similar setup. To get from the velocity to the displacement, we need to, again, integrate. So that's going to give us 1 minus 1.5 t squared plus 4, 0 times t plus another constant vector. And we're told that when time is 0, this position vector is 1, 1, so therefore c must be 1, 1, because when t is 0, those two disappear. So we're left with 1, 1. So s is 1 minus 1.5 t squared plus 4, 0 t plus 1, 1. And we're asked to find the position of P when t is 3. So we need to plug in t is 3 into that. So s when t is 3 is equal to, we're going to have 9 plus 12 plus 1 is 22 in the I direction. And then in the j direction, we've got minus 13.5 plus 0 plus 1. So it's minus 12.5. It's a position vector, so leave it as a vector. Job done. Question 2. A wooden crate of mass 20 kilograms is pulled in a straight line along a horizontal rough floor using a handle attached to the crate. The handle is inclined at an angle alpha to the floor, as shown in figure 1, and we're told that tan alpha is 3/4. The tension in the handle is 40 newtons. The coefficient of friction between the crate and the floor is 0.14, and the crate is modelled as a particle and the handle is modelled as a light rod. Using the model, find the acceleration of the crate. Okay, so it's moving along the horizontal floor. So that means vertically, we're not going to have any movement, which means the forces up must equal the forces down. So let's just resolve vertically first of all. So resolving vertically, we've got forces up, we've got 40 times sine of alpha. Okay, that's the upward component of this force, plus the reaction force of the table onto the box, floor onto the box. And that must equal the weight, which is 20 times 9.8. Okay, don't use 9.81, you will lose a mark in A-level maths. Now it looks like we've got two unknowns here, we've got alpha and r, but actually we're told that tan alpha is 3/4. So what we can do is quickly draw out a triangle. There's my alpha, that's 3, that's 4, by Pythagoras that's 5. So sine alpha is 3/5. Okay, opposite over hypotenuse. So actually this number here is 3/5. So 40 times 3/5 is 24. So we have 24 plus a reaction force. That's going to equal 20 times 9.8, which is 196. So subtract the 24, and we end up with R is equal to 172 newtons. That's the reaction force, and we need that because we want the friction force. Okay, using the coefficient of friction of 0.14. Okay, that'll allow us to resolve in the horizontal direction. Okay. So resolving horizontally now then. Forces to the right, we've got 40 times the cosine of alpha, That's going to be in the positive direction. In the negative direction, we've got the friction, which is mu r because it's in motion, so friction is at its maximum. So it's 0.14 times the 172 that we just got. And that needs to equal the mass of the block times this unknown acceleration. So this is now just a linear equation in A, because we know that cos alpha is 4/5. In the same way, we knew that sine alpha was 3/5. So 40 times 4/5 is 32. 0.14 times 172 is 24.08. And that needs to equal 20A. So we're going to have 32 subtract 24.08 all over 20 gives us 0.396 meters per second per second. Okay, the crate, let's go back to the question, that's part A, 6 marks. Part B, the crate is now pushed along the same floor using the handle. The handle is again inclined at the same angle, alpha, to the floor, and the thrust in the handle is 40 newtons, as shown in figure 2 below. Explain briefly why the acceleration of the crate would now be less than the acceleration of the crate found in part A. Okay, so we're not going to do any calculations, just as explained briefly, we don't need to do any calculations here. And the answer to this is because the force in the handle now has a downward component, which increases the reaction force, which will increase the friction. Or something of that ilk. Okay. So the idea to talk about here is that because this is now pointing slightly downwards into the table as opposed to pulling upwards, the reaction force will be greater because you've now got the weight plus this downward force. So the reaction force will be greater, which means the friction force will be greater because F equals mu r. Whereas here, because this had a component going upwards, the reaction force decreased from the 20g, which meant that the friction force decreased as well. Okay, so yeah, friction is going to increase, which means the acceleration will be less. So friction increases, implies acceleration decreases. Okay, because the horizontal force from here is still the same, it's still 40 cos alpha. Okay, question 3. All right, a small stone A of mass 3m is attached to one end of a string, and a small stone B of mass m is attached to the other end of the string. Initially, A is held at rest on a fixed rough plane. The plane is inclined to the horizontal at an angle alpha, where tan alpha is 3/4. So actually, it's exactly the same angle as we had in the previous question. The string passes over a pulley P that is fixed at the top of the plane, and the part of the string from A to P is parallel to the line of greater slope of the plane. Stone B hangs freely below P as shown in figure 1, and the coefficient of friction between A and the plane is a 1/6. Stone A is released from rest and begins to move down the plane. The stones are modelled as particles, the pulley is modelled as being small and smooth, and the string is being modelled as light and inextensible. Okay, so that's the setup. Using the model for the motion of the system before B reaches the pulley, write down an equation for the motion of A. So go back to my diagram, I'm going to annotate this. It says it's moving down the slope. So there you go, stone A is released from rest and begins to move down the plane. So it's going to move this way, so that means it's accelerating that way. So I'm going to take that to be positive, and when I come to it in a minute, I'm going to get that as positive. I've got a tension in the rope, and I've got a weight acting downwards, which is going to be 3mg. Okay, the mass times the acceleration due to gravity. Okay, so I'm going to resolve down the plane. Oh, hold on, we've got friction as well, because we said it's rough, haven't we? There we go, the coefficient of friction between A and the plane is a 6th. So I've also got a friction force in there as well, so it means I need the reaction force. I'll call that R. Okay, so write down an equation for the motion of A. So it just wants the equation for this part. So I'm going to resolve down the plane. So I'm just popping that notation in so that the examiner knows what I'm intending to do here. And we're going to have all the forces in the positive direction, which is going to be 3 mg times sine of alpha. Okay, if that's alpha in there, then sine alpha will push it down the plane. So 3 mg sine alpha minus the tension in the rope minus the frictional force. That's going to equal the mass, which is 3m, times the acceleration, which is currently unknown. Okay, I think that's probably about right for 2 marks. I don't think you'd need to do F in terms of R, but I'm sure that'll come in the next part of the question. Okay, but B. Show that the acceleration of A is a 10th g. Okay, so this is where I now need to consider what F actually is. So because it's moving, it's starting from rest, but it is now moving, F is going to equal F max, which equals mu R. Okay, so I need to calculate R. So I'm going to resolve perpendicular to the plane, so it's going to be up in that direction, and I'm going to have R is equal to 3 mg cos of alpha. And again, we know that cos of alpha is 0.8 because of tan of alpha being 3/4. So that is 0.8 times 3, which is 2.4 mg. So that's my reaction force, and mu therefore is that divided by 6. F max, the frictional force, is that divided by 6 because mu is a sixth. So we're going to end up with that, which is 0.4 mg. Okay, so that's my frictional force. All right, so if I plug that now into here, this gives me that 3 mg times sine theta, which is 3/5, minus the unknown tension, minus the frictional force, which is 0.4 mg. That's going to equal 3 ma. And that's 0.6, that's 1.8. So 1.8 mg minus 0.4 mg is 1.4 mg. And that's going to equal the tension force plus 3 ma. So that's one equation linking T and A. M is also an unknown, but we'll get back to that, I'm sure. The other equation, I need to use B for that. Okay, so at B, what forces do we have? Well, we have the tension force going upwards, and we have its weight, mg, acting downwards. The tension force is the same because the pulley is described as smooth. So that value of T is across the 2. Oh, that's not underlined, that's just me explaining. So I'm now going to resolve vertically at B. So that's going to give me T minus mg equals ma. So that's going to give me, the second equation now. Okay, there's T again, and then there's A again. So I need to solve these simultaneously to find A. I don't know M either, but when I cancel the T's, actually the M's will disappear. So this is going to tell me that 1.4 mg equals T, but T is ma plus mg plus 3ma. Okay, so that ma plus mg there, that is the T. I've just used this definition of T into there. I can divide through by m now, and I get 1.4g minus another g. Yeah, that's 0.4g is equal to 4a. And that tells us that the acceleration is 0.1g, which is g on 10, which is exactly what the question said, as required. So these questions are quite nice because it kind of confirms your answer, okay, because the answer is in the question. Okay. Show that the acceleration of A is a 10th g, which is exactly what we've just done. Okay, part C. Sketch a velocity time graph for the motion of B from the instant when A is released from rest to the instant just before B reaches the pulley, explaining your answer. Okay, so the acceleration is g on 10. That's a constant acceleration, and it wants a velocity time graph. So therefore, we don't have any blank paper, so I'm just going to do it down here. And therefore, we're going to have a graph that looks something like this. That's my time. That's my velocity. So constant acceleration. That implies a linear velocity. And we're told that t equals 0, v equals 0, and that was given in the question. Okay. That does say initially it's held at rest. So initially the velocity is 0. Part D, in reality the string is not light. State how this would affect the working in part B. Okay, so we've got a string that's not light, so so therefore we must consider the mass of the string, which we've not done, and the mass of the string, well, that's going to increase down here as time increases. So we're going to have, what's going to happen? We're going to have a variable tension. Yeah, I think tension might vary slightly. I wonder what the answer is in what it's actually looking for. Yes, the tensions are different. Yeah, so the tension's going to vary. And that's because as the string kind of goes around the pulley, you get more mass on this side, and the tension's going to vary throughout the string. So here it's having to hold up the weight of that string as well as the mass, whereas the string here is only going to have to hold up that bit of the string plus the mass. So it's got less to pull up. So the tension's going to vary throughout the string. You will never be asked to model something like that mathematically on this course. Fortunately, all tensions are constant on the A-level course. Okay, question 4. A plank AB of mass m and length 2a rests with its end A against a rough vertical wall. The plank is held in horizontal position by a rope. One end of the rope is attached to the plank at B, and the other end is attached to the point on the wall at C, which is vertically above A. A small block of mass 3m is placed on the plank at the point P, where AP is x, and the plank is in equilibrium in a vertical plane which is perpendicular to the wall. The angle between the rope and the plank is alpha, where tan alpha is 3/4. That's a very popular angle in this paper, clearly, as shown in figure 3. The plank is modelled as a uniform rod, and the block is modelled as a particle, and the rope is modelled as a light inextensible string. Using the model, show that the tension in the rope is this thing. Okay, so what I'm going to do is I'm going to take moments. I'm going to take moments about this point here. Okay, moments about A. And the reason I'm going to take moments about this point is because then the reaction forces at the wall are negated. They're completely ignored. So the only forces we've got are the weight of the plank, the weight of the mass, and then the tension in the string. And then I can rearrange to give the tension as the subject. Okay. So to illustrate what I'm going to be doing, for part A, I'm going to take moments about A, and if you write that, the examiner is going to know kind of what you're attempting to do. So we've got two forces acting down on this side. So down is going to be a clockwise motion. Assuming it's a uniform plank, let's just check. Yes, that's equilibrium. There we go. Plank is modeled as a uniform rod. Okay, so because it's uniform, it means we can assume the mass of the plank is in the middle of the plank. So the length of the plank is A, which means the mass of the plank acts at A, all right, because the whole thing is 2A. So the distance from here to the centre of mass is A, and we are told the mass is M. So A times M, that's the moment of the weight, plus the distance, x times the weight of that thing. Oh, there's a g in there. Now the weight of that thing is 3 mg. Okay, the mass is 3m, so the weight is 3 mg, and times that by x. So 3 mgx, and that's going to equal the tension in the string. But I need to split that out into a horizontal component, which is going to have a 0 moment, and a vertical component, which is going to have a 2a times that figure moment. So it's 2a times the tension multiplied by the sine of alpha, and the sine of alpha is 3/5, because tan of alpha is 3/4. Okay, so that now gives me an equation with just t in it. I just need to rearrange and hope it comes out as the answer given in the question. So I've got the m, the g, and the g can combine to factor out. So I've got mg into a plus 3x. And I need to divide that by the coefficient of t over here, which is 2a times 3/5. And that's going to equal t. All right, so I'll factorise the mg on the top, divided by 2a times 3/5. And now neaten that up, so times top and bottom of that fraction by 5. I get 5 mg into a plus 3x divided by 2 times 3 is 6a, and that equals the tension. And that is exactly what they've got here, except the 3a and the 3x and the a have swapped over. That's fine. So as required. Okay, part B. The magnitude of the horizontal component of the force exerted on the plank at A by the wall is 2 mg. Find x in terms of A. So we're told that this force here is 2 mg. Okay, the horizontal force. And it's going to be pushing back that way because the tension is pulling it that way, and they need to cancel out because those are the only two horizontal forces. So with that in mind, let's actually resolve horizontally. And we're going to get 2 mg must equal t times the cosine of alpha, because that's the horizontal component of the tension. So that is going to be 0.8 t. Well, I've got t, so I can plug that in. So I get 2 mg is equal to 0.8 times that, which is 4/5. So that's just, that 5 is going to change to a 4. So I get 4 mg into a plus 3x divided by 6a. Okay. And now the mg's will cancel. And what does it want? Find x in terms of a. So I'll just make x the subject of this. So I'm going to times that up, get rid of the mg's, and then we're going to get rid of the 4 as well. So I'm going to get 3a is equal to a plus 3x. Okay, so 4 over 6 is 2/3. The 2's will cancel, the 3 comes up, and the mg's have disappeared, and the a has come up. Okay, so it'll be 3a, and then I've got the a plus 3x left. And then I could just subtract a and divide by 3. So x is equal to 2a on 3. So it's 2/3 of the way along the plank. Sorry, it's 2/6 of the way because the plank is 2a long. Okay. The force exerted by the plank on the plank at A by the wall acting direction makes an angle beta with the horizontal. Find the value of tan beta. So we've got the 2 mg acting this way, but there's also going to be a vertical force acting that way. If that's negative, hey ho, it doesn't matter. It just means it's acting downwards. We've got the vertical forces, the y, the weight of the plank, the weight of the box, and the tension. So I just need to resolve vertically here. So part C, resolving vertically at the plank. We've got y plus t sine alpha, which is 0.6. So that's all the forces acting up. And that's going to equal all the forces acting down, which is mg, which is the plank, plus 3 mg, which is the weight, or the block. So that clearly comes to 4 mg. So y, which is the vertical force acting at the wall, is 4 mg minus 0.6 t. but I've got t, that's up here still. So times up by 0.6, that 5 gets changed for a 3 now, and 3 over 6 is just 2. So that's going to be minus mg into a plus 3x, but x is 2a on 3. I know you can't see it, but I'll be there in a minute. All divided by the 2a. Okay, so that's what I get. So there's my tension. It's times by 0.6, so that 5 got changed for a 3, which 3 over 6 became the 2 on the bottom. And then I've also replaced the x there with 2a on 3, as we found in part B. So what we should find is that the a's there cancel, and we're left with y in terms of mg, which is good, because then we can calculate the angle, because we've got capital X in terms of mg. Okay, so that's 4mg minus 3 times 2/3 is 2, so we got a plus 2a, which is 3a. So 3a over 2a is just 3 over 2, so it's minus 3 over 2 mg. So we've got 8 halves minus 3 halves is 5 halves, so 5 over 2 mg. Okay, so that's the vertical force at the wall. Combine that now with the horizontal force. That was 2 mg, that was 2.5 mg, and the both of those together is going to give me that 2.5 mg. So tan of beta, which is what the question is asking, is going to be opposite, which is 2.5 mg, divided by adjacent, which is 2 mg. The mg's cancel, so we're left with 2.5 over 2, or 5 over 4. So 5 quarters, so just over 1. Which is good. There we go. So 5 over 4. And the rope will break if the tension in it exceeds 5 mg. Explain how this will restrict the possible positions of P. You must justify your answer carefully. Okay, so go back to here. The box is now varying again. Okay, the box is not just at x is 2 on 3a. It's now anywhere. So we go back to this definition of the tension, where x varied. And we cannot have that exceed 5 mg. So T must be less than 5 mg. So for part D, for T must be less than or equal to 5 mg. This implies that tension 5 mg into a plus 3x, all divided by 6a, must be less than or equal to 5 mg. Okay, so the tension is less than or equal to 5 mg, otherwise it's going to break. The 5 mg's will cancel. Okay, we can divide those because it's a positive number, so it's not going to affect it. So we're going to end up with a plus 3x is less than or equal to 6a. Okay, again, a is a positive number because you're going to have negative length. So I can times by it, so that's fine. Subtract the a. So x must be less than or equal to 5a on 3. So this says if x is between 5a on 3 and 2a, can't be more than 2a because that's the edge of the plank, then the rope will break because the tension will exceed 5 mg. Therefore, x is restricted to 0 is less than or equal to x is less than or equal to 5a on 3, so 5/3 a. So it does restrict the motion of the box. Okay, if this came out to be something bigger than 2a, then it wouldn't matter. But it hasn't, so it does matter. It does restrict the motion of the box. Question 5. The points A and B lie 50 metres apart on horizontal ground. At time t equals 0, two small balls P and Q are projected in the vertical plane containing AB. Ball P is projected from A with speed 20 at 30 degrees to AB, and ball Q is projected from B with speed U at angle theta to BA, as shown in figure 3. At time t is 2, P and Q collide. Until they collide, the balls are modelled as particles moving freely under gravity. Part A. Find the velocity of P at the instant before it collides with Q. Okay, so this is going to be a SUVAC problem in 2 dimensions, because it's just a projectiles question. So looking horizontally and vertically. Horizontally, its distance is, let's call it x, and let's call that vertically y. U horizontally is 20 cos 30, but cos 30 is root 3 on 2, so maybe that's just 10 root 3. And vertically is 20 sine 30, which is 10. V, well, that's going to vary with time, so we'll just leave that. Acceleration horizontally is 0, because we're not modelling any resistances or anything like that. And vertically it's minus g. Okay, I'm taking up to be positive, so therefore acceleration is downwards. And t is t. And what does it want? Find the velocity of p. So I need v as a velocity. So the velocity, v equals u plus at. So we get that. And I'm looking for the velocity when t is 2, because we're told it collides 2 seconds. Yeah, because they're both projected when t is 0. Okay, and they collide when t is 2. So, velocity when t is 2 is equal to the u, which is 10 root 3, 10, plus the acceleration, which is 0 minus 9.8 times 2. Okay, so that's going to give us the velocity of p. And 10 root 3 plus 0 is still 10 root 3. And 10 minus 19.6 is minus 9.6. And it's asked for the velocity, so therefore we leave it as a vector. Job done. Okay, that's velocity of P, the instant before it collides with Q. Okay. That seemed to be easy for 6 marks. Oh well. Part B. Find the size of angle theta. Okay, so what is x? So let's use s equals ut plus a half at squared to get x and y. Okay, this will give us the coordinates of where it collides in the between a and b. So xy at the point when t is 2 is equal to 10 root 3, 10 times 2, so that's u times t, plus a half a, which is going to be 0 minus 4.9 times t squared, so it's times 4. So that's going to come out to be 10 root 3 times 2 is 20 root 3, and I get 20 minus 19.6, so it's 0.4. Very, very close to the ground, actually. Okay, let's go with it. All right, so now we know where it is when t is 2. So, see that again. This time it's going to be for q. Horizontally, I'm taking that way to be positive now, and vertically. So horizontally, well, for these two to have collided, then the displacement in the x direction for this one and the displacement in the x direction for this one must sum to 50, because they're 50 meters apart. So because this one travelled 20 root 3 in the x direction, then this one must travel 50 minus 20 root 3, so that they sum to 50. Vertically, well, they're both going to have travel the same vertical distance, okay, 0.4, because they're both colliding and they both start at 0, so they're both going to be travelling upwards to 0.4. Initial velocity is u cos theta horizontally and u sine theta vertically. I don't know the final velocity. Acceleration, again, that's 0 minus 9.8. And the time is... Can you close that door, please? And the time is t is 2. Okay. So we're going to have s equals ut plus a half AT squared, because that's the CVAT equation that doesn't contain a V. So it's going to give us two equations with U and theta in them, and then we can solve them simultaneously. So we're going to have 50 minus 20 root 3, 0.4, is going to equal U, which is U cos theta, U sine theta, times 2, so 2 of those, plus a half AT squared. So that's going to be plus 0 for the top one, and then minus 19.6 for the bottom one, because t is 2. So that gives us two equations there. So 2u cos theta equals 50 minus 20 root 3, and 2u sine theta. That's going to equal 0.4 plus 19.6, which is 20. And we can solve those simultaneously. If I divide one by the other, I will get tan of theta equals 20 divided by 50 minus 20 root 3. So that will give us that theta is, which is what part I want. I get the calculator. It's in radian mode, so we'll just convert it at the end. So we're going to have inverse tan of 20 divided by 50 minus 20 root 3. And then to convert it back to degrees and do times 180 over pi. So that's 52.5 degrees. And then I can plug that back into one of these to find u. So that's going to be 20 divided by 2 times sine of that answer, which comes out to be 12.5 meters. And those are both to 3 significant figures. I will just check that answer with this one here. So I'm just going to inverse cos. It's going to be 50 minus 20 root 3 divided by 2u, which is my answer. That should give me 52.5 back. Times 180 on pi. There, yeah, close enough. Okay. And then state one limitation of the model other than air resistance that could affect the accuracy of your answers. So air resistance we can't mention. So say wind could move the ball. What else could be said? Question 5. Spinning. Or the side of the ball. So any of those 3 answers were fine. Only one of them needed. And that completes the paper. Okay. Hopefully you found that useful, and I will be doing videos on everything else, so statistics, the core pures, and further mechanics and decision. So keep your eyes peeled for those, and yeah, if you have any questions, then come and ask.